This problem is a simple frame, the sort of thing you might see in a supermarket or B&Q type store. It's got some loads on it, maybe due to wind loading, and the dimensions are as we see here. Key point about this structure is that it's got two pin supports, so left and right at the bottom, but it's also got an internal pin at C at the apex, and this internal pin is crucial to the analysis we'll do here, as we'll see in a moment. So, as always, the first thing is to draw a free body diagram, which we can do like this. The external loads we know, they're easy, we can just draw those. And then, because it's two pin supports, there are four unknown forces acting on the structure, and it's these four forces we need to determine. Worth noting at this point that we've got four forces, but only three equations of equilibrium. This is clearly going to be a problem, because if you've got four unknowns and three equations, then you won't be able to find all the unknowns. We've got a solution, so we'll keep going and see what happens. So the first thing we're going to do is, as normal, take moments. We'll take moment about A. We know there's 0 moment there because it's a pin. We've got the first term in the equation, 10 times 3 is the moment due to the point load. The second term in the equation is the moment due to the distributed load, acting in the opposite direction, anti-clockwise. And then finally we've got the moment due to the support reaction, VB, which is what we want to find in this case. If we work that through, then we find that we've got the support reaction, that's 33 kilonewtons, so that worked fine. Second stage, we'll consider vertical equilibrium, so we'll look at forces acting vertically. Again, we know the frame is stationary, not accelerating, so the overall force is 0. And it turns out this is pretty straightforward. We've just got the two support reactions. We know VB, VA we didn't know, but we can work it through, and it's the opposite, minus 3.3 kilonewtons. And then finally we've got horizontal forces to consider. Again, we know there's equilibrium horizontally, but it's here that we find we've got a bit of a problem, because this is our final equation of equilibrium, which we can apply to the whole frame, but we've still got two unknowns, HA and HB. So what are we going to do? Well, at this point it's worth noting the pin again, and remembering that equilibrium applies not only to the whole structure, but to each part of it. So what we're going to do in this case is to consider the equilibrium of the right-hand side of the structure, so the piece with the distributed load on it. And so we're going to draw a free body diagram just of the right-hand side. If we do that, it looks something like this. So we've got the HB, which we want to know, we've got the applied forces, and initially it doesn't look that promising because we've got two unknowns at the pin and the moment, which we do know to be 0. But if we take moments, those two additional unknowns don't come into the equation. So I'm going to take moments about the apex, or point C, and see what happens. So moments about C is 0. We've got the distributed load giving us a clockwise moment, and then we've got two terms, one due to the vertical reaction and one due to the horizontal reaction, HB. And rather conveniently we find we've got one unknown in this equation, so we can work that through. And what we find is that the horizontal reaction, HB, is 3.56 kilonewtons. So this is good, because if we now take the final equation we had on the previous slide, when we had two unknowns, we've now solved for HB, and so it becomes simpler, because we can now write it just with the one unknown in there, and once we've got one unknown and one equation, we can solve that very easily. So we've solved the problem. We've discovered what all four reactions are by applying equilibrium firstly to the whole frame, and then secondly to a part of the frame. And the way we were able to do this was because of the pin at the support. If that pin hadn't been there, if the members had been rigidly connected, then we wouldn't have been able to solve this problem using equilibrium alone. We'd have to use more advanced techniques, which we'll come to in later years. There's a similar problem to this, which is a 3-pin arch on the tutorial sheet, and it would be worth having a go at that, having seen this video.